All right, so let us recapitulate what we have done thus far. So in our treatment of time-dependent perturbation theory, so these are all applications, but so here it is. So what we have basically discussed is the interaction of atoms with radiation, right? So suppose if we shine light on atoms, then we have discussed that two possible things can happen. The atoms can absorb a quantum of light from this radiation as long as the energy of the radiation, energy of the quantum is exactly equal to the energy difference between two levels. Then this particular absorption can cause a transition between the two levels. So an atom can absorb a quantum of light of energy h nu and be excited from a lower lying energy state EI to a higher energy state EF. So this is stimulated absorption. Another thing that can happen is the atom can, in the presence of external radiation, the atom can de-excite from a higher energy state to a lower energy state, giving out. So the arrow in this case is the other way around. So this was a mistake. So giving out a quantum of light to the external radiation, again, as long as the difference between the energy levels is exactly equal to the frequency of the incident, the energy of the incident radiation, right? So these are the two aspects that Fermi's golden rule neatly encompasses. The only difference between the rates of these transitions of stimulated emission and stimulated absorption lies in the delta function. So as you can see, the factor of 2 pi over h bar times the matrix element of the perturbation between the unperturbed states mod square of that is exactly the same between the two, but the delta function changes. Of course, if the delta function changes, all your integration and things like that do change. But anyway, this is important to keep in mind. The prefactor is the same for both of them. The only difference is whether you are exciting the atom or de-exciting the atom. So the first is exciting the atom is absorption, de-exciting the atom is emission. So this is the cases of stimulated emission and stimulated absorption, and this is quite easy to understand in some sense, right? So this is what one would expect to happen in the presence of an external radiation. So in the case of ionization, we treated the external radiation, external electromagnetic radiation, as a classical electromagnetic field. And then we wrote down an effective Hamiltonian for the time-dependent perturbation as A dot P. Of course, the time dependence comes from the A part, which is actually a time-dependent function, right? But in the perturbation A dot P, right? So where was that? There, the boxed equation. In the perturbation A dot P, the A part was treated as a classical field. Okay, so in our discussion of ionization, this is what we did. And this was more than enough to account for the kicking out of electron from an atom, which is ionization, photoelectric effect. So there was actually much before the full advent of Schrodinger's and Heisenberg's quantum mechanics, Einstein had actually thought about these processes of spontaneous emission and spontaneous absorption. But he has also thought about one very important thing called spontaneous emission. Okay, so we will talk about what Einstein's idea was and how is it related to what we are talking about. So Einstein's A and B coefficients. In fact, Einstein's original paper about this is something that I will link to in the Google Classroom site. I strongly encourage everyone to read it because it is actually quite easily understandable. Okay. So Einstein also was thinking about these ideas of what happens when atoms interact with radiation. Okay. Of course, Einstein and like many other physicists in those times, was an expert on classical electromagnetic theory. And this was just about the advent of modern quantum mechanics. I think this paper that Einstein wrote was around 1916 or so, just when he was finishing up his general theory of relativity. And this is a very instructive paper. So Einstein starts by detailing that three different things can happen when you place an atom in an external field, external electromagnetic field. So he claims that the atom can absorb. So suppose if there is, so he doesn't talk about an individual atom, of course, because he was driven by the ideas of statistical mechanics. So he thought of a whole bunch of atoms, and many of them can be in state 1, many of them can be in state 2, so on and so forth, whatever it is. So let us assume that you immerse this complicated system in an external electromagnetic field. Okay? So Einstein claimed that three different processes can possibly happen. Suppose if you have a bunch of atoms in this gas in state M, right? They can absorb radiation and excite themselves to a state N. And this is exactly what we have discussed as stimulated absorption. He also claims that a bunch of atoms in state M, a higher energy state, can de-excite to a lower energy state N, okay, in the presence of external electromagnetic radiation. And this is also what we have discussed. This is stimulated emission. But he also claims that there is also a rate at which an atom can de-excite from a higher energy state to a lower energy state, regardless of whether you have an external electromagnetic radiation or not. And he called this, or this is now known as spontaneous emission. So let us actually write down the three different processes and Einstein's nomenclature for this, which has become now standard in the literature. So the point is, you are putting a whole bunch of atoms in an external electromagnetic radiation. So Einstein defined a quantity AMN. Okay. Okay. So this is not showing, so I'll have to reshare again. Sorry, give me just a second.
So just a quick question. So the Einstein postulated these things, or he derived these mathematical formulations at the time?
So Einstein had no idea of Fermi's golden rule or time-dependent perturbation theory or anything like that. This was much before quantum mechanics even. So at this point, when Einstein did it around 1916, Planck had proposed the idea of quantum and the whole history of blackbody radiation, as you know, right? So Einstein's motivation in this had nothing to do with spontaneous emission as such. That was only a component of his idea. He actually wanted to see if he can derive Planck's blackbody radiation formula, the energy density of blackbody radiation that Planck had derived. Einstein wanted to place it on firmer quantum mechanical grounds. So that was his guiding motivation, as you will soon see. Of course, we will not follow Einstein's derivation to the letter, because whatever he does is applicable to all kinds of radiation, but he was typically interested in blackbody radiation. So he wanted to derive Planck's spectral formula. Okay, so that was his motivation. But
it just came out of his mind, like he thought about it.
Yeah, no, it didn't just come out of his mind. So like many other physicists in that time, right, Einstein was thinking very deeply about these issues of quantum mechanics, the birth of quantum mechanics, literally, right? So blackbody radiation had been around for a while. And actually, Planck did not initially give a derivation of his formula. So let me actually talk about that for just a second before we move on to this. So remember, oh my gosh, so this is my my Bluetooth is really misbehaving today. Okay. So remember that in the turn of the century, scientists were really interested in blackbody radiation, right, for various historical reasons. Blackbody radiation is basically, you just assume that there is a cavity, right? I'm sure you guys know about this very well, but I'll just recapitulate. There's just some kind of a cavity, right? And then you drill a very, very small hole and you put in light inside. Okay, this is an approximation to a black body. You just coat this with anything that is quite dark, and all light would do is suffer internal reflection and will be completely absorbed by the walls of this black body, right? And then, of course, once it is absorbed, it will emit radiation, the thermal radiation, and that is the spectrum that we want to study. So, what is um, the relation between the frequency of this light and the temperature of the external radiation? So there was a formula that was proposed. So by the way, almost every body radiates heat, right? So you and I and everybody that is listening to this lecture or not listening to the lecture is also radiating. Of course, at room temperatures, the radiating heat is actually very, very minimal, and the frequency lies probably in the far infrared. So it's not probably easy for us to understand. That's why we don't glow. Right? But that is not true for a hot metal or something. If you keep heating up a metal, of course, it gets hotter and hotter, and then it starts giving out frequencies more and more from what? From the red to violet, right? And finally, it just becomes white hot. So that there is a connection between frequency and the temperature is fairly obvious, but what was not obvious is what is the energy density of this radiation, of this emitted radiation. And towards the end of the 20th century or 19th century, sorry, no, 20th century, Rayleigh and Jeans had this famous formula. They had a formula for rho of nu T. Okay. So give me a second. Just let me actually give me a second. Let me actually reconnect my iPad because there seems to be something terribly wrong with the Bluetooth at the moment. Okay, so let's see if this works. Okay. Okay, good. So Rayleigh and Jean gave a formula for rho of nu T, but of course their formula was such that if you integrate this energy density over a whole bunch of frequencies from 0 to infinity, the energy density basically diverges, right? And this came to be known as the ultraviolet catastrophe. So Planck came along and he basically said that, wait a second, assume that the black body cavity, the outer wall of this cavity, is made up of a whole bunch of resonators, right? And these resonators can only absorb and emit energy in certain quanta of energy, which of course we all know by now is h times nu. And then based on this hypothesis, he basically hypothesized that the energy density of this black body radiation has to be something like 8 pi h over c cubed. And there is a famous nu cubed divided by e to the h nu over kBt minus 1, where kb is the Boltzmann constant. Right? So initially Planck did not give a derivation for this formula. It was basically just desperate guesswork. But later Planck gave sort of a very laborious and lengthy calculation that it sort of derives this rho. But from the modern standpoint, this is not a very illuminating derivation. So there is no point going through that. So basically, many people in those times were interested in this formula. So we were trying to understand whether this formula can be understood from first principles. And Einstein's A and B coefficients was actually, in the historical context, an effort or an attempt to understand this blackbody radiation energy density formula from a quantum mechanical standpoint. Okay, so that is the historical context for Einstein's idea. Is that clear?
Yes, sir.
So Einstein basically thought that if you put an atom in external electromagnetic radiation, three things can happen. There can be stimulated emission, there can be stimulated absorption, and there can be spontaneous emission. So when I talk about stimulated emission and stimulated absorption, this should depend upon rho, right? This energy density of the external electromagnetic radiation. Now, regardless of what the external electromagnetic radiation is, so this is an external radiation for a black body, but it could be anything, any random radiation, whatever it is. All these three processes can still happen. Okay. For the case of stimulated emission and stimulated absorption, the rates of these transitions should be proportional to rho, the external radiation. But for spontaneous emission, it is independent of whether you place the atom in the radiation or not. So the spontaneous emission rate should be independent of rho. This was Einstein starting. So he starts his discussion by claiming that there is three different kinds of rates. The first rate he defines is the quantity AMN. This is the rate at which an atom will spontaneously make a transition from a state M to a state N of lower energy. Okay, so this has no counterpart with what we have done thus far. What we have done thus far is always interaction of atom with radiation. But this claims that there is no external electromagnetic radiation. And the word external is important, and I'll tell you why it is important toward the end of this lecture. So this is the first rate that he defined. The second rate that he defined was BMN rho of nu comma T. What is this? This is the rate at which an atom in a radiation field, external radiation field, will make a transition from a state M to a state N of lower energy. So this is the same as before, except that this emission rate is proportional to the external electromagnetic energy density. So remember that there is two quantities here, B and rho. Rho is dependent on temperature because the external electromagnetic radiation is basically thermal radiation. So it is a function of both nu and T. The B is a completely atomic property. So just like the A, which is a completely atomic property, the B is a completely atomic property, and all dependence on temperature and radiation is encapsulated in the energy density rho. Okay. The third is this is of course stimulated emission, as you can easily guess. The last one is BNM rho nu T. What is this? This is rate at which an atom in a radiation field, I'll specify that explicitly, makes a transition from a state N to a higher energy state M. Okay. So this is spontaneous emission. This is stimulated emission. And this is stimulated absorption. Okay. So I'll underline these three. So the question, really the most interesting question, at least from a historical perspective, is why did Einstein think of spontaneous emission? Right, and this is something that I'm also trying to understand right now, looking at many papers in the literature. Stimulated emission and stimulated absorption are fairly straightforward. This is suppose if you're a classical physicist, you know that this is what can happen if you put an atom in an external electromagnetic field. But spontaneous emission is a completely different beast. It tells you that even if there is no photons around, an atom can still de-excite. Okay, from the modern point of view, this happens because there is no external electromagnetic field, but you really cannot switch off electromagnetic field completely because the atom itself is a source of electric and magnetic fields, right? So atom itself is composed of an electron, so there is electric and magnetic fields present in the atom itself. So there is no way you can put an electron, an atom, in a space where E and B is absolutely equal to 0, because the atom itself generates an E field that you cannot possibly switch off, right? So this is the source of spontaneous emission from the modern point of view, that it is still interaction of an atom with electromagnetic radiation, except the electromagnetic radiation is a self-electromagnetic radiation. From the classical physics point of view, what drove probably Einstein towards spontaneous emission was the fact that even classically there's a radiation reaction force, right? So there is a self force that one can calculate within classical electrodynamics. I'm sure that you have seen this in your course on classical E&M, and it is this that probably causes these transitions between higher energy states, lower energy states. But if you look at Einstein's original paper, it seems that he was also motivated by radioactivity. And this is also something that I'm trying to understand. So he basically claims that, this is obviously the same as radioactivity. Radioactivity has to do with some instability, of course, right? So because there is excess neutrons or protons in an atom, and of course such atoms cannot live for long, so they basically de-excite and become something that is more stable. Of course, the next question is, what is the source of this instability that Einstein probably thought, and it probably has to do with the fact that there is a radiation reaction. Anyway, whatever the reason.
So this electromagnetic force that you're talking about, that we cannot isolate electrons with electromagnetic fields. So these are with the interaction of the electron with the protons, or by electron itself.
So suppose if we have an electron, see, atom is electrically neutral, of course, right?
Yes, sir.
But if you think of the electron itself, and so suppose if you look at an electron cloud, right? And then if you measure the electric and magnetic field around the electron cloud, it won't be equal to 0, right? So the fact that atom is charge neutral doesn't mean that there is no electric and magnetic fields themselves, individually speaking. So have you guys done the self force or the what?
We did it in the classical electrodynamics course last semester.
So from a classical E&M point of view, this is exactly what is happening. So suppose if you look at a radiating point charge, a point charge that is accelerating, that will automatically radiate, right? So we can think of this radiation. What is radiation? Basically, it is leaving out energy in the form of some kind of a radiation, right? So this radiation is what you can think of as causing spontaneous emission. In fact, there's a whole history of this subject and a lot of literature. And I should admit that I'm also not very well versed with this literature. And I'm just looking at some of these papers as preparation for this lecture. And it seems rather interesting because there have been attempts to simply calculate the rate of spontaneous emission simply by assuming a classical radiation reaction. Okay. And it seems that you're off by a factor of half. And then you can look at a quantum mechanical view of things, and basically you can use quantum field theory to calculate spontaneous emission. So I'll tell you how to do that, or at least the idea behind it toward the end. But strictly speaking, you can actually understand this even within the classical physics viewpoint. Basically, you claim that the source of radiation is because you have a point charge that is accelerating, and of course it is emitting radiation, and this is the radiation that is causing the decay itself. Okay.
And so does this spontaneous rate depends on how many other electrons are present in the atom, the interaction with them?
So yes, of course, it is basically something very complicated, right? So I cannot derive a closed form expression for AMN right now. So suppose if you look at a very complicated atom with very many energy levels, very many electrons, of course the electric field is a very, very complicated object. So, but that is not what I'm talking about. As long as in principle the power radiated by these accelerating charges is calculable, all I'm saying is that this power radiated can be a source of radiation that can itself cause spontaneous emission. So yes, I mean, in principle, it will be very difficult to calculate what the electric field is or whatever it is, but you can always calculate the power radiated, right? So it's
Yes, sir.
for at least hydrogen-like atoms, it should be not very difficult. Anyway, so this was Einstein's starting point. So he claims that all these three different kinds of processes can happen. And at equilibrium, the rates of transitions from this higher state M to a lower state N would be equal to the total transition from the lower state N to the higher state M. Of course, this is the definition of thermodynamic equilibrium, because you have an atom that is in equilibrium with the external path, right? So let us assume that at any time t, let there be Nm atoms in state M and Nn atoms in state N. Okay. Oh my gosh, again, for the fourth time today, I'll have to reshare. Okay, good. So let's just get through this fast so I don't have to keep resharing. So basically, thermodynamic equilibrium simply states that the rates of transition from the state M to state N, state M, I remind you, is the state of higher energy, state N is a state of lower energy. Rates of transition between M to N should be the same as transitions between N to M. So there is two different kinds of transitions that take you from M to N, that is spontaneous emission and stimulated emission. There is one kind of transition that will take you from state N to M, that is stimulated absorption. So let us equate these two rates. Of course, for every single atom, the rate is AMN and BMN. And if you have a whole bunch of atoms, it will be the number of atoms times the individual rates. That is the total rate. So the total rate from M to N transitions would be Nm times the spontaneous emission rate plus the stimulated emission rate, which is proportional to the external electromagnetic radiation. In thermodynamic equilibrium, Einstein argued that this has to be equal to the transition between N to N. Okay. Now, of course, the nu here cannot be arbitrary. The nu here has to be actually the difference in frequency, because the transitions can only happen if the energy of the radiation matches the difference in the energy levels, right? So the next step in Einstein's idea was to apply classical Boltzmann statistics. According to Boltzmann statistics, and I don't have to motivate this to you guys because you're studying statistics now, statistical physics now, so you're experts at this. The number of atoms in the state M divided by the number of atoms in state N at any time is equal to e to the minus Em minus En over kBt, right? In other words, the statistical weight assigned to any state M is e to the minus Em over kT, okay, with some proportionality constant, which is, as you know, is 1 over the partition function. Of course, if you take the ratios, all such proportionality constants get cancelled, and the only thing that survives is the e to the minus E over kT part. So in other words, since Em minus En would be equal to h nu nm, the quanta of radiation that is emitted or absorbed, this ratio would be equal to e to the minus h nu nm over kBt. Okay. So plug everything in nm. So in this boxed equation, I'll box this equation. Okay. So take nm to the other end, and you will write this. You can rewrite this equation as amn rho of nu. I'll actually be explicit and write this as rho nu empty, because it is not any random nu. It is the nu that causes these transitions to happen. This is equal to e to the minus h nu nm over kbt, sorry, plus, because this is n over nm, times bnm rho. Okay, is this clear to everybody? So if there's any questions, please stop me and ask. Which means I can now relate the rate of spontaneous emission to the rates of stimulated emission and stimulated absorption. So AMN equals rho times e to the h nu over kBT BNM minus BMN. Okay. So at this point, let us pause and remind ourselves that the quantities A and B are only properties of the atom. They cannot depend on temperature, right? And they have no idea, they are not properties of the external electromagnetic radiation. So which means A and B, whatever they are purely atomic properties. So they cannot be temperature related quantities. But of course, we seem to have a complicated relation between AMN and the B's, which is temperature dependent. Of course, that was not our starting point. Our starting point was to say that we made sure that all the dependence on rho is factored out in these rates, right? Like here. So how do we understand this equation? The way we understand this equation is ask ourselves, under what context can we get a temperature independent relation between the A's and the B's. Okay. Now, at this point in the derivation, this relation is true no matter what your electromagnetic radiation is. But at this point, not Einstein, but at this point, let us specialize to blackbody radiation. In other words, let's assume that the radiation that we are talking about, the atom is immersed in actually a blackbody radiation field, which is 8 pi h over c cubed nu nm cubed divided by e to the h nu nm over kBt minus 1. Okay, so let us assume that this is the particular radiation that we are talking about. Now look at this equation that relates A and the B. Under what condition would you have, suppose if I plug this in, I will have AMN equals 8 pi h over c cubed over kBt minus 1 times e to the h minus BMN. Okay. Now let us ask, under what conditions would the relation between the A's and the B's be temperature independent? There is actually a peculiar, a unique relation that emerges, and this would happen if the two B's were the same. If the two B's were the same, remember that I can pull out a common factor of B, and the bracket is e to the h nu over kt minus 1, which exactly cancels this denominator. Okay, does this make sense to everybody? So if
Yes, sir.
BNM equals BMN, then we have AMN actually equals 8 pi h over c cubed nu nm cubed times BMN. Okay, so this is the way in which Einstein heuristically understood the relation between the coefficients of stimulated emission, stimulated absorption, and spontaneous emission. Another way to say the same thing is as follows. So let us assume that you keep increasing the temperature of the field. more and more, right? In the limit t goes to infinity, what happens to this equation? The limit t goes to infinity, of course, e to the h nu over kt becomes 1. So so AMN is basically something times BNM minus BMN. But what happens to the denominator? The denominator becomes 0, right? So which means you have something that is blowing up, multiplying BNM minus BMN. And the only way you can manage the situation is if you argue the two B's are the same. So this becomes identically equal to 0. But of course, this is a cleaner argument that I just gave you, that if you want these coefficients to come out temperature independent and only as properties of the atom, this is a unique solution. So these are the Einstein A and B coefficients. And the remarkable thing about these coefficients is that knowing the rate of stimulated emission or stimulated absorption, Einstein basically said you can calculate the rate of spontaneous emission. So knowing the rate of stimulated emission, you can calculate the rate of spontaneous emission. Okay. So this is, of course, not at all obvious. It is highly counterintuitive because stimulated emission is a property wherein the atom de-excites in the presence of an external electromagnetic radiation. Spontaneous emission, at least from a classical point of view, happens when the de-excitation of the atom happens when there is no electromagnetic radiation present. And it turns out that the rates of these two are actually calculable if you know one of those two. Okay, so this was the magic of the Einstein A and B coefficients. And this is all from a very classical standpoint. But this idea that knowing stimulated emission, you can actually calculate the rates of spontaneous emission is actually true, even in the quantum theory. Okay, so this was all basically pre-Schrodinger equation, right? So this was in the 1916s. So what is the modern perspective about this? The modern perspective about this is that, so modern viewpoint is that in the Hamiltonian that we have, the perturbing Hamiltonian, which is, I think, minus E over 2 MC A dot P, right? This was the Hamiltonian that we had, if I'm right. Anyway, I'm sure the A dot P is right. This is the coefficient. I'm not sure, but I think it is okay. So for the ionization part, we did a semi-classical approximation. What was a semi-classical approximation? Basically claimed that the atom is a quantum mechanical object, but the radiation in which it is immersed is a classical object. Well, we cannot get away with that viewpoint for spontaneous emission. If we want to understand the rates of spontaneous emission, we have to calculate it from first principles. You would have to take the course to what is called quantum field theory. Okay, so you'll have to quantize the radiation to understand spontaneous emission rate, to understand or to calculate the rate of spontaneous emission. We need to quantize the electromagnetic field as well. Okay, there is no getting around this fact. So we cannot treat A as a classical object and just claim that P is an operator. We have to basically claim that A is also an operator. That is what is meant by quantizing the electromagnetic field. So what do you typically do? You write A, okay, as a linear superposition of Fourier. So basically a Fourier decompose A. Okay, so 1 over some root V, where V is some kind of a volume in which you immerse this radiation. And then I'll tell you what these sums mean in just a second. A k lambda, epsilon lambda, e to the I, k dot r minus omega t, plus a k lambda, star epsilon lambda star e to the minus I k dot r minus omega t. Now, what is k? K is the wave vector. And what is lambda? Lambda is the polarization. So as you know, electromagnetic fields can have two different kinds of polarization, two transverse degrees of polarizations, which means epsilon lambda is a vector that characterizes these two degrees of polarization. Lambda runs from 1 to 2. Okay, lambda equal to 1 to 2. K is the wave vector. Of course, it can be anything it wants to. But suppose if I put the electromagnetic radiation in a box, okay, and apply periodic boundary conditions, of course, I can decompose A as a Fourier series in this particular fashion, okay? Of course, this is true even if I'm doing quantum field theory or a classical field theory. This is also true for a classical field theory. There's something very peculiar about this. Quantum field theory basically tells you that these Fourier coefficients A and A star should be treated as operators. Okay, so QFT tells you A k lambda and A dagger k lambda, not A star, are operators. And their operators very similar to the A and A dagger operators you encountered in your simple harmonic oscillator. Okay, basically A dagger creates a quantum of photon with momentum k and polarization lambda. A k lambda is an operator that destroys a photon with momentum k and polarization lambda. Okay, so the way you actually do quantum field theory is, of course, you get rid of all these boxes and you replace the summation over k by an integration, of course. So let us assume that there is some normalization, which I will not worry about. D cubed k over 2 pi cubed, 1 over square root of 2ek. Again, this comes from some.
Sir, how do we obtain this expression for A that you've written?
I'll come to that in just a second. So this is some a k lambda epsilon lambda e to the I k dot r minus omega t plus a k lambda dagger epsilon lambda star e to the minus I k dot r minus omega t. Okay. So basically, A and A dagger are operators. Okay, just like your simple harmonic oscillator operators. Of course, A dagger creates a photon mode with momentum k and polarization lambda. A operator destroys a photon with momentum k and polarization lambda. Okay. So, and then you basically apply canonical commutation relations between A and A dagger, just like you do in quantum mechanics, except that in the case of, say, like you do in simple harmonic oscillator, except that unlike the simple harmonic oscillator, there is an infinite number of A's and A daggers, one corresponding to every possible momentum value. What are the possible momentum values of a photon? Well, it can be infinitely many. Okay, so that's why there is an infinite number of A's, one which acts on every possible values of K and lambda. Okay. Anyway, so that's as far as I will go as regards to quantum field theory. Now, the question is, why can I write A in this particular fashion? This has to do with the fact that A obeys, even classically, A obeys a wave equation, right? See, A obeys the equation. What does the magnetic vector potential obey? So if you remember your electrodynamics course, you would guess that A is d square A over dt square minus del square A equal to 0, right? Because there is some 1 over c square. Yeah?
Yes, sir.
So the solution for this is basically, one of the solutions is a plane wave, right? Now I can write this solution as a superposition of plane waves. So A equals e to the I k dot r minus omega t is a solution of this equation. Agreed?
Yes, sir.
With, of course, c equal to k times omega, right? So if this is a solution, then I can write superpositions of this. There is also a solution. Agreed?
Agree.
So suppose if there is 5 different k values that I can think of, I can sum over all these 5 different k values and write this. And this will also be a solution. Okay.
So here in this the formula that you written, what is k? Like k is going over all the values from infinity, minus infinity to plus infinity.
Which formula?
this summation that you've written, a summation over k in A of R T.
Here in this formula.
Yes, sir.
So K can be anything that you want. So
So,
suppose if I put the electromagnetic radiation in a box and apply periodic boundary conditions, then K can, of course, K will take only certain values, right? Because you have to respect the boundary conditions, right?
okay.
But if I don't do that, K can be literally anything. So here it is a summation over K and not an integration, because I'm assuming periodic boundary conditions. So remember your particle in a box problem. In the particle in a box problem, you want the wave function to go to 0 at both the ends of the box, right? So that quantizes the possible values of momentum that the particle can take. Agreed? Hello?
Yes, sir.
So this is exactly equivalent. Suppose if you put a radiation in a box and apply periodic boundary conditions, then the momentum would be quantized as some 2 pi n over L. So the sum over K in this is basically a sum over n, a discrete index n. Of course, there is no restriction on the possible values of n. N can go from 0 to infinity. Of course, in quantum field theory, you don't really put radiation in a box or anything, because quantum field theory is valid all over space-time. So in this case, K is actually a continuous variable. In this, the second formula for A of RT that I've written down, K is actually a continuous variable. Okay, where K can go from literally minus infinity to infinity. So basically, to understand spontaneous emission, I can start with the same Hamiltonian, perturbing Hamiltonian A dot P, but I would have to assume that A is actually an operator and not a classical object. Okay. So I'll stop here for today, and then we will continue tomorrow, where we can discuss a little more about this if there is any questions, and I'll also tie up some loose ends that have cropped up in the last week. Okay.